these little curly braces indicate a set. The elements in that set are 1, 2, 3, and 4. So I just want to make sure we get our terminology down. Now, in order for a set to even have any kind of meaning and for us to work with a set, it has to be well defined. Okay? Now, before I even tell you what that means, let me just throw some examples at you, because I have a feeling you're just going to know. Right? So, how about something more obscure? All of these are sets. We're just going to talk about them one at a time. I figured I would just get them all written down first, and then we'll go back. Now, if at any point I start talking too fast or writing too fast, just let me know. And I can slow down, and you guys are always welcome to interrupt me at any point. So I haven't actually told you what I mean by well-defined. But just kind of looking at that set, is there any one of these that maybe jumps out to you and you're just like, yeah, that's not well-defined? Like without me even telling you what it means.
E.
Which one?
The big numbers.
Ooh, this one?
Yeah.
What do you guys think? What makes that one not well-defined?
It's vague.
It's
Yeah.
vague,
Yeah.
right? That's exactly what this means, right? So not well-defined means it's vague, that there's a question as to what's in this set, what's not in this set. That's what I mean by well-defined. Well-defined means there should be no question if something's in that set or not. So let's start with A. Is this one well-defined? Is it crystal clear what's in that set?
Yes.
Yes. So is that set well-defined? Yes. What about the set of months? Now, that's just me being lazy and not writing January, February, March, April, May. So is that clear as to what's in that set?
No.
Why not?
Well, because you have 1568, the months are 1568.
Oh, no, totally separate set. Don't look at this.
Oh, I'm tweaking, okay.
Yeah, that was okay. No. That was done. So now just the set of months of the year.
Yeah.
Yeah, no question as to what's in there. Hot days.
No.
Yeah. Right?
What's hot?
What's hot?
Oh.
Ah, see, what's hot? Hot to some person, I mean, are we talking hot to someone who's from Chicago, or are we talking to hot from someone who's from Florida? Because those are two different hots. So that is not well defined. However, look at the next one.
Yeah.
That one's well defined, right? So if you want to say hot days, okay, what does hot mean? Okay, let's say that you define hot as 80 degrees or higher. Now we're well defined. We already said big numbers, no. What's a big number? What about the set of even numbers?
Yeah.
Yeah, that one's good. We know what's an even number. So things have to be well defined in order for us to be able to talk about that set. Now, there are ways of writing sets. So we have a descriptive way. That's where we just kind of list everything out. That's just kind of a brute force. Like, let's just say I'm talking about 1, 2, 3, 4, 5, 6, dot, dot, dot. Do you guys know what I mean if I put a dot, dot, dot here?
Keeps
Mhm.
going.
Yeah, the pattern keeps going. If I don't have a dot, dot, dot there, then it stops at 6. Now, this can also, in this kind of descriptive, this is also what's called a roster, that list. I didn't pick a very good one for descriptive here.
Would descriptive be like the words too, like when you said
Right.
days when the temp was, that's descriptive?
Yeah.
Okay.
Yeah, with this one, I could just say the natural numbers, yeah, just a set of natural numbers. So yeah, let's do that instead. That's a little messier because you guys have to know what the natural numbers are. So the natural numbers are the ones that are like 1, 2, 3, 4, 5, 6. The whole numbers start at 0 and then go 0, 1, 2, 3, 4, 5, 6. The integers are like all of the whole numbers and their negatives, so you'd have to know all that terminology. So I really lean a lot toward the roster notation. The descriptive, I would only use it if it's something I feel confident that you guys would understand. And then we have something called the set builder. The set builder is the ugliest. The set builder would be like X such that. Yeah, it's the ugliest of the 3. You may have seen this before. This little line means such that. I really dislike this notation. I feel like it's just sexy for no reason. You know, I mean, yeah, it looks impressive, but this would say that this is a number such that that number is an element of the set of natural numbers. Really, the difference between the roster and the set builder, a lot of times just has to do with this X such that business. So really what you can kind of do in this set builder notation is you can almost ignore that part right there, and it's just either like a descriptive or a roster. So if that part right there is what's bothering you, then you can just ignore it. Come back to this. I mentioned this a minute ago. looking at those two sets, this set is infinite. That set is finite. So how can you tell the difference between those two?
Because it's not continued, the finite one is not continued.
Right,
Yeah.
finite meaning stopped. Infinite meaning not finite. So it keeps on going. So let's talk about one more kind of set here. That set has nothing in it. So we call it the empty set. There's nothing in it. Empty set does actually show up. So it's not something that we're gonna have to ignore. It's gonna keep showing up. You can also use that symbol. You guys seen that symbol before for the empty set? But you can't use them together. So one or the other. Don't use them together. That is not the empty set. That is a set. See, I got the set notation? That's a set with a symbol in it. That set has one element inside of it. So that's a set with one element. So be careful, you just have to pick which one you want to, that you want to use, which one of those symbols you want to use. All right, so let's talk some more about the set notation and put some of this terminology together, okay? So I mentioned earlier, that weird little E business is a symbol that means is an element of. That just means, is this contained in that set?
Yes.
That's a lot of what math is. It's just another language. So this is asking you, is the letter D part of that set? Yes, it is. So we would say yes, so that's true. So now that you know how to read that symbol, that goofy looking little E there,
No.
this is just asking you, is G an element of this set?
No.
No, it's not a trap. Is G in that list? Nope. Okay. Here's where it starts getting a little more confusing. Notice I put a line through that.
Is not?
That exactly
Right.
means is not an element of. So this one's a thinker. H is not an element of this set. So H is not in that set. Is that a true statement?
Yeah.
Yes.
Right. Maybe one's a little goofier. How about? So that one I used a descriptive set instead of just the roster notation. I don't know if you guys recognize what that is. That's a Greek letter theta. I was trying to pick some goofy symbol.
Hmm.
So is theta a letter of our alphabet?
No.
No. So that would be false. One more. This one's going to be even more of a thinker here. Because I know Alex is going to throw some of that set builder notation at you. I'm going to throw some of that at you as well.
So X is 15, right?
Well, yes, in this case, yeah.
Okay.
X is actually any number
Okay.
that is a natural number. That's, okay. So let's translate this. Here's what this is saying. Remember how I said this X such that? You can just ignore that part. This is whispering little sweet nothings to you, and it's telling you, hey, I'm just looking at these numbers. So that's what that natural numbers is saying to you. And then also, so it's a natural number, and what is that saying to you? And it's greater than 2.
So X is always what is outside the set, like what's by the
Over here?
Yeah.
Not necessarily. In this one, because our set has a lot of things in it. So this set right here, if I were to list it out, it would be 3, 4, 5,
Yeah,
6.
everything greater than 2.
Yeah, exactly. Everything greater than 2. These are the exact same set.
But it's true because X is greater than 2.
So 15, because 15 is greater than 2.
Yeah.
Yeah, yeah, so you're right, so it's true. So look at how much prettier it is to write 3, 4, 5, 6, ... as it is to write this. But they mean the exact same thing. This is just a way, way sexier math way of writing it. You guys never thought that word was gonna come out in math class, but.
Hmm.
The
Can you go back one?
oh, sure. Now, the reason I didn't include 1, 2, 3 was because it's the natural numbers that are also at the same time bigger than 2. So if I just said numbers bigger than 2, there's a lot more numbers that are bigger than 2. Because then you get all those decimals and those fractions in between those numbers.
So the N with the slash remains the natural numbers?
Yeah, yeah, so the N with the little slash is the symbol for natural numbers.
Oh.
Have you guys ever seen the real number symbol? You know, it has like, it's an R with like 2 legs to it. That's pretty common that we will have feels like that with a couple of legs to it. So like this one is all the real numbers. That one's all the natural numbers. Usually just use a regular old W. The integers are all the whole numbers and their negatives. And one might think integers, she's gonna use an I. Nope, it's a Z.
What's the Z again?
That's the integers.
Oh,
Not sure why. But the integers are all those like dot, 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 -3, -2, -1, 0, 1, 2, 3, da, da, da. I don't use that one all that often. The number of things in a set, the number of elements in a set is called the cardinality. I feel like in this section that nothing in here is like super complicated. It's just all really confusingly written.
Mm.
You know, like the questions are really straightforward. They're just written with so much symbolic stuff and so many big words that it throws you off. Now, we write the cardinality by saying the number of things in a set. So that's like saying the number of things in set A. The number of elements. The parentheses don't mean multiplication. They're like a function. You know how we always say with functions, f of x. This is the number of things in A. Over the set builder stuff.
So can the calculator do this type of thing?
It cannot.
Okay.
That's a good question. No. It could if those were numbers that you could put in there, but
Yeah.
if we have letters or words or something. All right, so I haven't actually given this set a name. I guess I maybe should. Let me just call this like set capital A. We tend to use capital letters to name set and lowercase letters for the elements. So how many things are in this set? Look, it's just 1, 2, 3, 4, 5. Like I said, this stuff isn't like hard, it's just worded so weird that you're gonna think it's hard. Right? If I just handed you that and said, how many things are in there? You're like, 5. What's the cardinality? I don't know, you know? So my job here is to make sure that you guys just know this terminology so that when you see it, you're like, uh-huh, trying to pull a fast one. Just call that next set B. Let's say that's going to be So our goal is just to write the cardinality of each one of these sets. So I just want to know how many things, the number of elements in set B. So how many elements are inside the set? The set being the little curly braces. 3. What? All right, remember, on those, that set builder notation, you can just kind of ignore that, pretend it never happened. All right, that's just telling you we're looking at 1, 2, 3, 4, 5, dot, dot, dot. This is where the good stuff's happening. This is telling you that you want all the numbers that are between 1 and 5. Including 5, but do we include 1? Why not?
It's less than or equal to.
Right, because there's no or equal to. So this is the numbers between 1 and 5. That includes 5, but not 1. So what is that gonna look like? So it's 2, right? 3, 4, 5. So how many things are in that set? Remember, we included 5 because of that little or equal to. I did not include 1 because of that strict inequality. It's strictly bigger than 1, not or equal to. What about that set? Which I forgot to label D afterwards. What's the number of elements in that set? Oh, be careful, it's just 0, not 0 with a line through it. That's a really good point. 0 is the number of things in there. The 0 with the line through it is the symbol for the empty set. And I say that because Alex will be picky-patty about this. And if you click on that little empty set symbol, it's gonna be like, nope, you're wrong, loser, try again. Now, if that happens, that, you do something like that, and let's say you accidentally, you make a little mistake like that, just email me. I can fix it. I can give you something. Because Alex can be like super picky. Good opportunity.
What's the 0 with the line through it again?
That's just another symbol for this.
Oh yeah, oh, okay.
Yep, so there's just 2 different symbols. One's a set with nothing in it, and the other one is just that empty set symbol. What about the set of oceans that touch Illinois? How many oceans touch Illinois?
None.
No.
None. Now, you would say that this is the same as the empty set,
Mm.
because there's not any. But yeah, with these cardinalities, you want to make sure that you're using the number.
And you wouldn't put a line through the O there?
No, you wouldn't.
Okay.
Because that's the symbol for an empty set, and this isn't asking you for a set answer. It's asking you how many things are in the set.
Oh, okay.
So yeah, it's a very tiny little difference,
Yep.
but yeah, and that is a really common mistake.
I'm when the 0 through is like this.
Yes.
Sideways?
Yeah, either way. I mean, no, not straight across, but yeah,
Yeah,
sideways,
that piece,
yeah.
that's not.
All right, so sets can be equal or they can be equivalent. Two sets are equal if they have exactly the same elements. I mean, that's kind of a duh, right? Here's the catch though. They can be in a different order. It'd still be. This is where it's not as obvious. Two sets are equivalent. If they have the same cardinality. That's the same number of objects. Alex goes through this a little more difficult. They'll say that two sets are equivalent if there's a one-to-one correspondence between the elements of one and the elements of another. Yeah, sure, okay. TLDR, the cardinality is the same. So here's what this means. Those two sets are said to be equivalent. They're not equal because they're not exactly the same. So they're equivalent since both of them have 4 elements. We're like, yeah, you are close enough. They're not equal though. Whereas if I did something like that, those two are equal since they have the same elements. So these two both have A, B, C, D. They're just in a different order, same elements. So these two that are equal, are they also equivalent? Like if equivalent just means they have the same number of elements, is it true to say that these two sets are also equivalent?
Yeah.
Yeah. So that's the thing, is equal is a stronger version. Equivalent is a lesser condition. So if two sets are equal, then they are also automatically equivalent. But not the other way around. So equal means exactly the same thing. So of course they have the same number because they have exactly the same thing in there. Equivalent, if I just tell you two sets are equivalent, that doesn't mean that they're equal. So it's really confusing with this terminology because in normal everyday speak, people use the word equal and equivalent interchangeably. And in math, they don't mean the same thing. So you just want to be really careful. So equivalent does not always mean equal. All right, so one more example here, and we will sets A and C are equal to each other. They have the exact same things in them, right? They can be in a different order, that's cool.
Oh,
17539, 17539, right? A and C. 13579,
yeah.
13579, they're there?
Mm.
All right, so that's true. What about B and C? Are those equal?
2, 4, 6.
No, those do
No.
not have the same thing. Now, equivalent has a symbol, just like equal has a symbol. Equivalent has a symbol, and you may have seen it before. It kind of reminds you of that approximately equal to, but that's the symbol for equivalent.
So you said things can be equivalent and equal at the same time?
They can,
Okay.
yes. Mhm. Equivalent is a much less strict condition. So it's completely possible to be equivalent but not have to be exactly the same.
Mm-hmm.
So equivalent just means, so all this is asking you, so that simple little statement right there just says the number of things in set B is 1, 2, 3, 4, 5. The number of elements in set C is 1, 2, 3, 4, 5. Because that's the same number, they're equivalent. Equivalent just means the two sets have the same number of elements. All right, last one. Are C and D equivalent?
No,
Why not?
because I don't have the same number of amount for each one.
Right, C has 5 things and D has 4 things. So remember that equivalent means the same number of elements. So this is very much a lot of terminology that, can really trip you up. But I'm hoping that the notes, and also when you're doing the homework and for these sections, if you get confused, you can always relive the magic and watch the video for this and say, okay, what did she say about equivalent and stuff? You can look at the notes online to kind of see where in the video I would be talking about this.
And the notes online are pretty much the same,
Yes.
right? Okay.
Yeah, I might just like grab some different ones here just to mix it up for you, but yep, they are basically the same thing.
Yep.
All right, well, I'll see you guys on Thursday maybe. You guys may show up.
Yeah.
Yeah, I know some people just learn